predefined format of this panel discussion, and we're going to have each one of those panelists to just actually introduce him or herself, and Jim, can you go first? Not so much with where you have been, but where you are now and then where you're in the future type of things. I mean, because one of us has got the bio, like already listed. So, okay. Anyway, sorry, made it too complicated. So
you did make it too complicated. You want me to say where we're going to go?
And then where you are.
Well, so where we are is we built 2 generations of AI silicon, and we're building a third with integrated Sci-Fi processors, which are pretty good. And we're building a new out-of-order processor, which we think is great. And we're started already, actually led by a Japanese engineer, our next generation, which we think is going to be a lot faster. And I'm interested in a couple of things. One is we want to figure out better about how AI and general purpose computing is going to work together. We want to raise IPC, and then we want to start to run programs that are really AI programs and design a processor for AI, because I think AI programs are going to run differently than standard current programs, and we think AI compilers are going to generate different kinds of code. And I think we want to be agile for that new kind of design point. So that's what we're doing.
Thank you. Wei-Fu is from like Red Hat, China.
Yeah. Thank you.
Yeah.
And so what we are doing is making the operation system more generic and can support the RISC-V server and desktop and AG system and automobile also. So in Red Hat, we have several products, and we also feedback to the open source community. So we're trying to make the software ecosystem more and more rich, can support the hardware, the real AI hardware in the future. So we made it stable and economic for the enterprise usage. Yeah.
Okay, thank you. Wei-Fu actually participated in an ARM integration of Linux for the long time, and then so later on, I'm going to ask like the Wei-Fu to just actually explain how RISC-V Linux, data center operating system is going right now. Okay, thanks. Omar, thank you. You got it.
Yeah, is this
okay.
on? Yeah.
Yeah.
So this is Omar Hassen. Actually, Travis couldn't make it due to illness, so I'm his replacement. And I run business development for Ventana. And over the past few years, we've built our first generation processor, which will sample the end of this year. And it's basically a great design that is competitive at the top end of performance across all the ISAs. So if you think of x86 and ARM, we're right there with them on performance. And we're well underway in our second generation design. And that design should be done by the end of this year, and we'll tape it out sometime in early 2024. And that's going to be a big step up in performance as well. So we are pushing the top end of performance within the RISC-V community and bringing RISC-V to be competitive with the other ISAs on performance. In addition, we've done a lot of work along with some of the other companies in the community on the software ecosystem. And as you've heard from everyone today, that we're well underway. The progress has been tremendous, I would say, given where we were and where we are today. And we feel very, very optimistic about where we're going. And you've heard our CTO, Greg Favor, talk in more detail about what we do, but we're focused on building the best RISC-V processor that we can possibly build. And we let our partners and some of our customers build their customization around it, be it AI or other accelerators, domain-specific accelerators that can accelerate different type of workloads. Thank you.
Okay, thank you, Omar. So I guess that while panelists are warming up, so I'd like to just actually talk about the purpose of this panel discussion, which is, I guess that I always admire people who just actually figure out why we are doing this in a larger context. And today, what we are, a lot of times we see engineers saying that I mind my own business, and then it's so much fun, and then so who cares? But often we have to think about a larger context that makes our profession possible. And this is, I guess that one of the why are we just actually working on AI processor essentially is, I guess that one of the thing is in Japan has got relatively high percentage of the power demand used for the data center even today, more so than in the States and more so than in Taiwan. And I don't give you exact figure, but it's relatively high compared to other countries. And if data center our utilization of AI, like ChatGPT, just actually increases, if that training of that machine just actually takes so much power, eventually we see world the Matrix, where human powers that the machine rather than the other way around, right? And here that these gentlemen have been working for many years to just reduce the power consumption of processors. I mean, Wei Fu was working on this ARM hardware so that he can reduce that power consumption per workload. And then I guess that one of the things about the Ventana is probably the same way. So I'd like to just actually first talk about the meaning of why we are attempting to go to the RISC-V, but thereby reducing the power. And does anybody want to make a comment on this?
Well, the most important power constraint is the power for the application. Like in your phone, well, I was one of the people that put an 8-watt processor in a phone, right? And 8 watts is way too much power for a phone. But what we found was it ran really fast and turned off really fast. So the user got a better experience because it was snappy. But the actual average power consumption wasn't worse. We just, instead of spreading 2 watts out over a longer period of time, we changed it. So whenever you're building a product, you have to say, what's the environment it goes in? So gamers, they can run big fans, and they actually like that because it put lights on the fans. And so we can build 95-watt desktop processors. We don't actually get that much more performance because that runs at high voltage, and people buy it for frequency. So that's not a really good use of power. But in the data center, there's a real limit to how much air we can blow over the processors, and that sets a hard power limit for each generation. So you trade off, if your processor's not efficient, you get less performance per socket, and we really have to worry about it. Now, the reason data center and AI power is going up so fast is because people want more of it. They get value from it. And I think it's going to be interesting when people spend money and power budget on AI to improve the design of other things where they might save power. So we'll see how that goes. I'm fairly sure there's about a factor of 10 improvement on performance per watt coming in the next couple of years based on better math, better precision, better power gating, and better optimization. And it's going to come from a bunch of things. But I still expect to see even higher power sockets because getting all the compute in one place is really important. And, you know, it's hard to say how it'll go exactly, but my guess is the percentage of the national budget for data centers is going to go up, and hopefully we save it in other places because of improved efficiency of the products we design with it.
Well, in your view, like what is the power used for machines rather than humans would be? Like what's the sort of percentage that?
It's not power used. Humans use the machines to do stuff they want, right? And the question is, what's the best trade-off? Like when we transition to electric cars, we get 2 to 3 times the energy efficiency per mile because electric motors and batteries are very efficient. So if we can build better products, then it's up to us to decide how to use resources to do that. And if computing lets us build better products, it's a net win on cost, which I think is the most important thing.
Okay. So does anybody want to pick up the same question?
Sure. I'll just add to what Jim said, just to bring it back to the RISC-V and chiplets level. We believe that RISC-V's flexibility allows you to optimize for workloads, and that creates power optimization. You can do what we call a coarse grain acceleration or optimization, whereby you can farm off the workload to a more optimized compute engine. Or you can do fine grain acceleration, where you accelerate based on certain instructions. So that should also help. The other one is chiplets, where you bring these different packages inside one package, and that basically allows you to use parallel die-to-die interfaces that are lower power. You save on SerDes conversions. So we believe that the combination of RISC-V and chiplets, alongside some of the other optimizations that were mentioned, are going to create a lot of more efficiency in the future.
What if you spent like 5 years trying to just half the power by going from like x86 to ARM? So maybe you might want to say something.
Yeah, actually, I come from an open source student. So for the power, and actually, we always been told in ARM why ARM will become will use in the data center because of power efficiency. But right now it's RISC-V. Because of the if we build an open source architecture, but still consuming more and more power, we will not really, survive and defeat or just compare with the other architecture. So even for open source, we still need to follow the business rule. We still need to consume less power than ARM and x86. That's what I get from the open source. Yeah.
Okay. So allegedly, like that, the RISC-V, by going to RISC-V from ARM, we're going to have yet another reduction of power. And is that really a true statement, or how does it sit with your view?
Well, RISC-V and ARM are pretty similar at the instruction set level. So it's not obvious that just as an ISA change, you get a power improvement. You really have to go think, are you designing the right computer for the application? And that's where things like combining CPU, I/O, network processing getting rid of SerDes, which is a high power, having much more optimized memory systems. I'm really interested. If you look at the roadmap that's happening for like much improved memory systems, I think we can save a lot of power there. On AI, well, over the next 5 years, AI is going to be the bulk of the power in the data center. Like this is happening pretty fast.
I see.
And AI can be hugely improved, and like we use RISC-V to drive the AI. So yeah, there's a lot of work to do this. But there's not a simple solution. Going from x86 to ARM was an obvious power savings, partly because ARM processors had always been optimized for power. All the RISC-V processors I know are optimized for power to start, but there's a lot of work to do.
I see. So you're saying that maybe that the side items, besides that the CPU, due to the fact that the RISC-V is open, you have a little bit more freedom, and then that.
Yeah, I think that's going to help. And then just end-to-end, better data, better power delivery, better data center design, better integration of all the components, and make sure you don't leave anything under-designed. Like very large memory systems with DDR is a very inefficient way to deliver memory because of power.
Okay. So that's pretty much that. Okay, now another thing is like that RISC-V going to data center requires like that actual development of the data center software. And then I wonder if you can actually describe where we are, you know, in actually porting of that various data center applications and so forth.
Yeah, in my opinion, it could be very fast, and we were very close to the deploy real RISC-V server into the real data center, because I don't know if you actually I mentioned it in my presentation there, and there's already have some server chip 64 core right now in the market, and the next year will be 128. And they are improved that year by year. And actually, we already enable some AI software and machine learning card combined with the 64 core system. So next year, they will really tape out some AI module MPU with the 64 core. So the development speed is very, very faster than we expected, actually. And actually, we are trying to catch up. For the software guy, we are trying to catch up the hardware implementation right now. So just from my experience, I think 2 or 3 years, we can see real RISC-V server and with the AI module, with the AI module in the data center. Actually, we are building that in China. Actually, some of the company already has chip and rack, the 2U server and rack put into the data center in this year. It will happen in this year. Some experiment system. Yeah.
So is China going earlier to like the RISC-V's data center than the rest of the world?
I think answer will be yes, because actually Chinese government will focus on the really open source stuff, put into the principle. I guess it's kind of, we can call it principle of the government. You know, this we encourage company and the university and student to learn about open source. So it will be development faster than the other, you know, area in the world. Yeah, that's what I guess. Yeah.
I guess that we're going to move to the next topic of how generative AI is related to increase of the power consumption, how that would play out in the real world, and if somebody wants to pick up this question, Jim, do you have some vision of like how everything will play out in terms of, well, particularly like that when we do have so much power going into data center, it's going to affect our power profile, power grid, how it is powered, whether we need to have a nuclear power plant and then that sort of stuff. And then maybe if you can give us like your vision of like how everything is going to be falling into places, that might be interesting.
Well, the first thing is like the revolutions that happened in the last couple of years, there's been multiple big changes, and it's happening pretty fast. And the AI researchers frequently find, since they're pushing today for better accuracy, better usability, better experience, that making it just bigger is the fastest way to do it. And the problem with that is making it bigger for 1 million users, they can do that. For 100 million users, they can't. There's not enough computers, much less power. But the situation is evolving pretty fast. And I think over the next couple of years, we'll find ways to solve the models to be much more efficient than they are. Now, whether that will be enough to solve the power problem, I don't know. I think building, modern nuclear power is actually a pretty good idea compared to the alternatives of coal and gas.
Mm-hmm.
So we'll see if that happens. That's not a computer problem mostly.
Yes.
Although we may in fact use computers to design much safer energy systems, and hopefully it will do that.
Mm-hmm.
But I think the evolution has been so quick, there hasn't been time to really spend the effort to optimize everything like it's going to need to be. And I think we'll see amazing improvements from just software optimization, and then there's going to be computer optimizations, which goes a little slower to run that. And that'll help a lot.
Okay, Omar, do you want to pick that?
Yes. So I just want to add that as Jim mentioned, the hardware will get better and the models will get better. Whether that's enough or not, we'll see. But there also could be changes to the business model of how AI gets deployed to the consumer, and that could also affect consumer behavior and how we deal with this problem as well. So again, there's multiple vectors here, but the tech community has been amazing at innovating and creating solutions. So I will not be surprised that if this problem gets solved in a very, very innovative and creative way. So we're very optimistic, and we're happy that people will need more compute cycles, and the combination of AI and general purpose compute will continue to be there. So I think this is the right time for RISC-V to break through, and the optimization, as we continue to mention throughout the day, that this hardware optimization will also drive that forward. So yeah, it's exciting. We'll see.
So I guess I go back to the software issues, but there's this as we all know that I guess that the Jensen is everywhere on the TV, and so that the CUDA is the thing of the today. And then interesting is like how are we going to transition from CUDA to something else, and maybe what is the scenario for that? If you can share with us that again.
Yeah, so this is an interesting point. So a couple of years ago, a friend of mine did a survey with AI researchers, and half of the AI researchers didn't know that CUDA existed, right? Because it's a low-level software framework, and most people, when they write AI, they don't write CUDA. They write PyTorch or TensorFlow, and then that calls the libraries. So CUDA it's an implementation language for low-level libraries, and it's actually not completely optimized for matrix multiply. We think there's better ways to do it. But it also shows up in lots of other pieces of software around AI for pre-processing images, and there's a number of pieces. So there's a couple of efforts. One is to make CUDA and OpenCL cross-compile, and that's pretty well known. The other is to improve, so the framework called Triton basically bypasses CUDA. So they generate assembly language code at a pretty low level for both AMD and NVIDIA. And we're going to write a version of our compiler so that you can hook Triton to that. So that'll take essentially CUDA out of the picture. But it's interesting that, like, in this day and age of writing amazing high-level languages, we talk about CUDA, because when Intel talks about their processors, they don't talk about writing in assembly language. Nobody writes in assembly language anymore. Well, maybe a few math library people, but it's very narrow. So in some sense, the funny thing about AI is we haven't defined what's called the hardware-software interface very well. In a normal CPU, RISC-V CPU, you can write a C compiler that gives you very good performance, and you always expect to use the compiler. Matter of fact, a lot of times the compiler can outperform any human, right? So the fact that CUDA is viewed as a thing we need to go work on means at some level we're solving the wrong problem. Like, the world doesn't need more assembly language programmers. We need more high-level language programmers. Mm-hmm. And I think that's the problem to solve that's better. And that's why having an open architecture so we can go modify how we build the computer to evolve to the place where then a compiler really works well. That's the goal. Not to copy CUDA. Because, like, RISC-V didn't say, well, we're going to copy the Intel architecture in assembly language, because that's actually part of the problem. So I think CUDA's the problem, and we'll have to solve it a different way.
Thanks.
Yeah, I think this, I'm not an AI guy, but I think they kind of like a standard, right? Just like if we build the module, build an AI module, we need a standard compiler, right? And something like that. So actually, the kind of standard is very important for the RISC-V right now, not just in the server rent, but also in AI. We cannot spread our force on different area, on different module, different NPU, and different implementation. We just need to focus on some of that. Then the ecosystem, the real software ecosystem, can be much better, and we can enrich that in some specific the good module. That's what I learned from the ARM development. Right? We need a standard for the server that we can have open box or out of box experiments. Yeah.
So we'll shift the gear a little bit. So, okay, there's this whole talk about Moore's law. Maybe we could pick up that subject. Okay. Do you want to go ahead and talk about this? The discussion that made you very famous.
Oh, did that make me famous? That was not it, no. No, it's really interesting, because Moore's law was a view about progress driven by a number of technologies. And, you know, photolithography went very quickly and steadily. And then as they went, they would hit speed bumps, and then we had to go invent new things. You know, copper wires, located dielectric, FinFET transistors. And then periodically you hit a stall. And then people decide, oh, because they're not making progress, Moore's law must be dead. But they're not looking at the fundamental thing underneath. And there's a question, how small can a transistor be? And it turns out it can be a lot smaller than it is today. There was a couple of years where everybody knew that flash devices couldn't shrink anymore, right? Because there were 25 electrons in a memory cell, and those electrons would tunnel out, and they would forget their charge. And then they invented 3D stacking, and it made the cell bigger, but then they stacked it, and they were 256 high. And the flash density went up hugely because they had the right invention. So Moore's law has clearly slowed down for the last couple of years. but it's not fundamental, right? What it's really requiring is invention to go solve it. Now, if people believe it can't be solved, the best way not to solve a problem is to believe it can't be solved, right? I think that's a bad approach. Like, we could say, well, we can't make AI more efficient, but nobody, so far people don't believe that. We think we can, so we're solving it. Yeah, we need more energy solving Moore's Law problems, and less energy having people get famous for saying that Moore's Law is dead, because that's crazy. And I said this at a TSMC talk. Does everybody realize that DNA is really great at sequencing atoms? Everybody know that? And the most power efficient computer in the world is the one in your head. And every single cell in your body has a factory that can reproduce a brain. It's unbelievably good. And people tell me Moore's Law is dead while they're walking around with 1 trillion machines that can assemble atoms more accurately than we can do in transistors. We already have the solution to it. We just don't know how to deploy it yet. Mm-hmm. And it's much, much better. DNA is actually, it sequences atoms so well, it's almost too small for building computers. Oh yeah, we'll see what happens. But yeah, I don't think Moore's Law is dead. I think that's silly.
The Moore's Law is not dead. Yes.
Sleeping with somebody, maybe.
How are we doing on the time?
Let's see. Sorry. 4 minutes left.
Okay, 4 minutes left. All right. So, okay. So again, I'm going to go insist on just actually having that, going back to that the social context of what we are doing. So for generic AI deployment, such as ChatGPT, data center power consumption is closely related to energy production, and then process scaling is actually related to building a huge fabrication plant, which actually does consume more electricity. And then, so while we are attempting to just go to try to get out of this like a carbon-based society, and everything is like a tied together in interesting circle. And how are we going to foresee our future? Is it going to be a better world, or what are the sort of like scenarios that we can think of in terms of our contribution to that society in general? Do you want to pick it up first?
Sure, I'll start. So I think you touched on a couple of important points, but to begin with, I think we all know that this movement is not going to stop. So just because AI consumes more energy, we're not going to stop doing AI. We're going to have to find a way. And again, it goes back to innovation, as was mentioned here. We have to invent new ways to be more efficient. We have to invent new ways to make more energy available in a not so harmful way environmentally. And at the end of the day, we're going to have to maybe change the way we think of AI as a business. And what we're doing here with RISC-V and chiplets is we're making our contribution. We're making the world more open. We're creating more possibilities for companies, customers of ours, to innovate and create new combinations of devices and technologies to solve these problems. So we are contributing by creating the tools for innovation.
You are?
I think from my work, from open source weight, we are trying to make the software more efficiency, and also actually this power consuming stuff is also the advantage of RISC-V because it's flexible, and people can use their intelligence to design more efficiency system. We don't have to rely on any company, any single company. Actually, in China, a lot of people working on RISC-V, more and more companies working on that. So they have their own solution. We don't have to, we don't have to have just one single solution. And from software, actually most of our software depend on how we're doing. So once we solve a hardware problem, we can have a better solution for software, and this connect with each other. So open source hardware with the open source software will be more efficiency than any limitation of specific architecture. Yeah.
I believe we should never waste energy, right? But we should generate a lot more energy. We should live in an energy-rich future. The sun puts enough energy on the planet for 100 times more energy use every day, without a big percentage of the Earth's covered with solar cells, right? Nuclear power, they've designed so much safer reactors, and we're not that far from fusion reactors. So I predict, the people who think we're running out of things should go outside more, look at the sun, and look at what science has done over the last 500 years, and start solving the problems instead of talking about it. Politicians don't solve problems; they just make them worse mostly. Like, this is a technical problem to generate more energy cleanly. Like, we know what the goals are. Clean energy is a requirement, but we can generate a lot more energy, and we should use it. And using 10 times more energy is probably a good thing. And then the models will be 10 times better, and the computers 10 times more. That's 1,000 times more computation that's going to happen over the next, somewhere like less than 10 years. I think that's going to happen. But if people shut down working power plants and do that, then we're creating shortages, but that's politics. That's not technology. So I think an energy-rich future is a much better way to go.
Okay. Yes. I mean, here in Japan, like, we had more nuclear power plant right after, like, for France. And I mean, the proponent of that nuclear power plant was saying that essentially, if you have more electricity, that generally, like, industry is going to be doing better, and then human life, like, it would be better. And that was the original intent of having so many nuclear power plant in Japan. And then I guess I hope that so this I hope that yeah, I think this is a little bit of censorship, so I should be yeah. But I mean, this is very interesting view. Thank you very much. I guess that this is a long time that you have listened to these things, but this is the end of the panel discussion. Do you have anything sort of to add in the end?
Thanks for having us all, and thanks everybody for coming. And spending the whole day. It's great.
All right. Okay, go ahead.
Yeah, exactly. Thanks everyone for coming. It was a very productive day. A lot of good presentations, and I hope everybody enjoyed the discussions. And we look forward to a bigger conference next time. Thank you.
Yeah, I'm so yeah. You have sense to the audience, so I'm gonna do the same thing. But that's the first time after the COVID I got out of my country, and 5 years ago I'm so happy to be here actually. And 5 years ago I sent there doing the very first Fedora on RISC-V presentation. In my entire life. So thank you very much to give me the chance to having me here. Thank you very much.
Okay, great. Thank you very much, everyone.
菅崎さんも意見あるんですよね、これ、イメールスタインさんって。